Hello everyone, welcome back to my YouTube channel. It's been a while since I last uploaded a video on this channel, so this channel has been dead pretty much for 3 years already. So right now I have a lot of time on my disposal since I recently finished my undergraduate studies and just recently I passed the ECE board exam. So the next couple of videos that I'm going to upload, it's about topics that I encountered during my board exam review that I found fascinating, but I didn't really have the time to actually derive them, or nor was it derived during the review. So it's a little bit random, but it's all going to be very interesting topics that we're going to try to derive and dive deep into. So for the first video, let's try to derive the coaxial cable characteristic impedance in a lossless condition. So in a lossless condition, we all know that the characteristic impedance is given by square root of L over C, wherein L is the inductance per unit length and C is the capacitance per unit length. We can solve for C since C is given by Q all over V, where Q is the charge and V is the voltage. We can also solve, V is not a vector. We can solve for voltage. It's given by the negative work done of an electric field over some path. And we can solve this electric field, solving for E, using Gauss' law. So in this case, we're going to use a cylindrical Gaussian surface. So for that, let's recall what Gauss' law is. So Gauss' law is the surface integral of the electric field. It's equal to the Q enclosed all over epsilon. So solving for the electric field and using a cylindrical surface, we get, so this is the area, 2 pi, the area of a cylindrical surface is 2 pi r L, and that's equal to Q enclosed all over epsilon. Solving for E, we then get E is equal to Q enclosed all over 2 pi RL E. Now, we need to find the voltage across these two terminals, D1 and D2, and you get that by integrating RE. So we have Q enc all over 2 pi RL E, and then we integrate that across R. So we have D2 all over D1. Then this becomes D1 D2 Q enc all over 2 pi LE times 1 over R dr. So this is the variable of integration. So it's going to be Q enc all over 2 pi L epsilon ln of D1 all over D2. This is our expression for the voltage across the coaxial cable per unit length. So this is. We then solve for C. C is given by Q over V. That's equal to Q enc all over this expression, Q enc all over 2 pi L E ln of D1 all over D2. Simplifying, we can cancel this one, and then we get an expression for RC as 2 pi epsilon all over ln of D1 all over D2. This is an expression for C. Alright, we can now then solve for the inductance. So for the inductance, solving for L, inductance is given by the flux all over current. So this dapat may end to, but let's just assume one loop. So inductance is equal to flux over current, and we can solve for flux as the integral of the magnetic field all over a surface. So this is the surface integral of the magnetic field. We can solve for B using Ampere's law, and we get B dot dl, so recalling Ampere's law, we get B dot dl is equal to mu times I. And then using a path, a circular path, so this is the coaxial cable, and then the magnetic and then the path that we're going to take is a circular path, since that is the direction of the magnetic field. So we get the magnetic field times the circular path, which is going to be equal to 2 pi r. It's equal to mu times I. So B is then therefore equal to mu I all over 2 pi r. So this is the magnetic field density. Let's then solve for the flux across the coaxial cable. So we're going to integrate B. Solving for flux, it's the surface integral of V all over a surface. So the surface is going to be this cross section. So the cross section is actually equal to so this ds, or the dA, it's going to be equal to dr dot dl. But then we know that dl is going to be just L, so it's going to be L times dr lang. This is the surface that we're going to integrate the magnetic field into. So flux is then equal to okay, let's make it formal. Let's just do dr dl. So this is the double integral of 0 to L, since this is 0 and then this is L. So the double integral from 0 to L, and integral from this is d1 and then this is d2, ui dr all over 2 pi r dr dl. All right, now we get, let's simplify this. Since wala namang L dito, we can just put L there, and then we're going to integrate this inner integral. So that's going to be equal to mu, dapat may I ito, mu I, doble itong dr. Alright, so mu I all over 2 pi ln of d all over, that's going to be d1 all over d2. This is equal to the flux. All right, so solving for the inductance, we get mu IL all over 2 pi ln of d1 all over d2. So we now have an expression for L, which is this one, and then we also have an expression for C, which is this one. Yeah, so you may be wondering what happened to the L here. I actually divided this already by L, since this is going to be in per unit length, so that may na-divide that to by L. So we're gonna do the same here. We're gonna divide this by L, so this cancels out. So we have that. So I'm just gonna rewrite the expression for C that we derived earlier. That was 2 pi E all over ln of d1 all over d2. Yeah, and then going back to the expression of the characteristic impedance in lossless conditions, we have ZO all over square root of L over C. So we have let's just do to the power of 1/2 here. So we have mu I all over 2 pi ln of d1 all over d2, and that's divided by 2 pi epsilon all over ln d1 all over d2. So this is going to simplify into 1 over 2 pi, square root of mu all over epsilon ln of d1 all over d2. And we know that mu is equal to mu naught times mu r all over epsilon times epsilon r. But then in dielectric materials, mu r is just equal to 1, so it's going to be ln d1 all over d2. So the expression that we have left is 1 over 2 pi times square root of mu r er. So these are relative permeabilities and relative, so these are relative constants. And then we have we have square root of mu o all over epsilon, but then we established that this is going to be equal to 1. And then grouping, we have 1 over 2 pi. We know that this is equal to approximately 120 pi. This is approximately equal to 120 pi. And then since we assume that mu r is equal to 1 in dielectric conditions, we have 1 over square root of epsilon r ln of d1 over d2. Simplifying this and turning it into logarithm, we then have this is going to be equal to 138 all over square root of epsilon r log of d1 all over d2. So how can you turn this one into log? You just apply change of base formula. So meron lang yang all over ln e, and then this is going to be the result. So other forms of this that was presented during my review, you can also express 1 over square root of er as the velocity factor. So 138 times the velocity factor log of d1 all over d2, and many other forms. But so that's how you derive the coaxial characteristic impedance. So sorry if this video was a little bit freestyle. I just wanted to try to derive some interesting topics, so I'm not gonna put an effort into making a script and all of that. So it's going to be a raw just sharing lang kung paano na-derive. So you guys, in case nakalimutan nyo during your board exam review, then you can derive it yourself if you have the time. Since during the board exam, super haba naman ng time. So that's it for this short video, and see you on the next ones where I'm going to show more interesting topics that I encountered during my review. So bye!